Hello metric students, welcome to our second lecture on chapter 12 from Real Econometrics, looking at limited dependent variables. So what I want to cover in this lecture is thinking about the marginal effects, and in particular we're going to focus on thinking through the marginal effects for a logit model. What I've drawn here is that S-shaped curve that we talked about in our last lecture. So previously we only had one variable that we were thinking about. It was just the spread. That was our x. Now we're going to be combining variables, and I'll explain in a second what we're going to do to make that happen. And we're going to use z to represent the combined variables. So what z is going to be defined as is just going to be the sum of our x's times our betas. So beta 0 plus beta 1 times x1 plus beta 2 times x2, onward and so forth. So z is going to depend on our x's. So you could think of them as having an individual value for z. What we're going to want to do is take our values for z and turn them into some sort of S shape. Now, in a separate lecture I might get into the technicalities of how that works and thinking about a latent variable approach. But right now we're just going to talk through the mathematics of how to do that and how to calculate the marginal effects in the case of the logit model. So the logit function is a function that takes this value and looks like this purple curve that is on our graph. And the logit function is a fairly mathematically simple function, unlike the probit function, which involves the normal distribution. It is just the e to the z over 1 plus e to the z. So this is how we're sort of connecting our x's and betas to this S-shaped function. And let's think about how this looks for certain values. At negative infinity, this gets super small, approximately 0. E to the negative infinity is 1 over e to the infinity, so it's basically 0, and so this entire function goes to 0. So as this moves to the left in our graph, it gets closer and closer and closer to 0. That's what we're saying here. What if the sum of the x's times the betas, or z, is 0? Well, anything to the 0th power is 1. So that means this fraction would be 1 over 1 plus e to the 0, which is 1, or 1/2. So when z is 0 at the origin, our function, our logit function of z, is going to be 1/2. Our final value that we'll think about is what happens as z goes off to infinity. This gets super big, infinitely big, as does our denominator. This 1 simply stops mattering. So what we essentially have is two equal things divided by each other, which is 1. So as z approaches positive infinity, our logit function approaches 1. So we can see our logit function is bound between 0 and 1. In the middle, when it is 0, our logit function is 1/2. So it's centered around that case where your 50% chance that you would, to use our example from last time, take the odds, and 50% chance that you wouldn't. That's how we are constructing this logit function. Now what I want to discuss is how changes in x influence the probability that y is 1. We are going to interpret our logit function as the probability that y is 1 that is how we're going to interpret the values of this function. So what we are going to question and ask here is, how does x, we could ask it about any particular x, so I am going to use the subscript j, impact the probability that y equals 1. So the probability that y equals 1 is what we're showing here in our y-axis. It's between 0 and 1. And we emphasized last lecture how moving a unit on the very far left side of our graph didn't have much impact on that probability, and it doesn't have much impact on that function. Similarly, moving a unit over here won't have much of an impact as well. The biggest impact is going to be right around this 0.5. So what we need to realize is there are going to be a couple things that are going to factor in to this question, how xj impacts our probability. The first is, well, what was our probability before? What was our value of z before? Where were we before we changed x? Unlike a linear model, where the impact on the probability is not a function of x, in our logit model, the change in probability is very much a function of not only x, but every single value of x. Not just xj, but x1, x2, x3, however many other x's there are. So that's the first thing to notice. The second thing is, if we're talking about maybe a 1 unit change, the impact here, it's going to depend on z. It's also hopefully going to depend on beta. So we can see that when we change x1, z is going to change by beta 1. So let's pick a point right here. Right, so this is, we're picking a particular value of z, we're picking it to be fairly close to 1/2. And if we're going to change x by 1, we're changing z by beta j. And this is the change that we are interested in. Now, there are 2 ways to think about it. We could actually do this calculation. So we could calculate this probability at this first point that I've sketched. And we could calculate the probability at the second point that I've sketched. And we could take the difference in those probabilities. That is a measure of how x impacts the probability at a particular point. Now the difficulty is that's not going to be symmetrical for an increase and a decrease. A decrease at this point would have a larger change in probability. If we're on the right side of z, a decrease is actually going to have a larger change in probability from this point. So we can also use calculus to talk about the continuous instantaneous rate of change at that point. In particular, we can take the derivative of our logit function with respect to our x value. You don't need to know how to take this derivative, but I want you to understand what we're looking at when we're talking about a marginal effect. We're talking about how x is impacted, how x impacts the probability. That's what this is capturing, and mathematically, so it's still e to the z, but on the bottom it's 1 plus e to the z squared times beta j. So this is a function of all of the other x's. It's a function of where you start. And then this is a function of our betas. So the only difference, if we change this from x1 to x2 to x3, this first component isn't changing. All that's changing is the second component of how much z is being changed. This is the marginal effect. Your marginal effect in the case where we have a logit model is very much dependent on your values of x. So it is individual. Everyone could have an individual marginal effect. The marginal effect for Bob, the marginal effect for Sue, it's all going to depend on where they are, how close they are to that inflection point of deciding whether or not to take the action. So one way to summarize these marginal effects, so these are our marginal effects. One way to summarize these would be to take everybody's marginal effect. All right, so look at all these different people and say, all right, that slope is that marginal effect. And we could take the average of all of those. So we could sum up all the marginal effects for each individual I and divide by how many individuals we have. So here we'd need to calculate every single person's marginal effect. I have you do this in the lab. So this is the average marginal effect. The other way that we could do this, which is computationally easier, is to look at all the values of z and then to take the average value of z. Maybe it's right here. Z bar is the average. And look at, for that average, for this z bar, this representative individual that doesn't exist, right? We're just saying we're taking the average of everyone's different characteristics and saying for that representative made up individual, what would the marginal effect be? That is the marginal effect at the average. So I'm going to erase this average marginal effect and going to write marginal effect at the average. And what we need to do to change here is the marginal effect at the average We're just plugging in a particular value of z, that average z. So this is the marginal effect at the average. We're looking at that slope at that particular point. So the last thing I want to look at is looking at some discrete changes in x. Sometimes it doesn't make sense to think of an instantaneous rate of change when we know a particular variable is a dummy variable. For instance, in our lab, we looked at whether the applicant was black and how that differed in terms of their probability of rejection. So what we're going to do is look at x1 as a binary variable. What makes sense to do is we can look at z for when x is 0 and when x is 1. Again, we could do this as an average marginal effect or a marginal effect at the average. So right now I'll outline how to do it at the average. So our z0 is going to be beta 0 plus beta 1. Now, instead of using the average value for x1, I'm just going to use 0. But for the other x's, I'm going to use their average, and so on. z1 is going to use, instead of 0, for x1, we're going to use 1. But for the other x's, we will use their average. So what we're going to look at is how does the probability differ between x1 and x2. Sorry, between our z when x is 1, x1 is 1, and our z when x is 0. So we're looking at the difference in these probabilities. And we can simply calculate the probabilities for each of these z values. This is why for the labs we did logit, because it is easier to actually do the calculations and fully understand what's going on behind the scenes. This is what Stata is going to report when you ask for marginal effects and when it knows that your variable is a binary outcome variable. This is the difference at the average for that discrete change in x1. One final way to think about how xj impacts the probability. So we looked at how a 1 unit increase impacts the probability. For the average, we looked at that for an individual. But oftentimes, as we've seen, a 1 unit increase isn't the right thing to look at. It's often interesting to think about how our x variable varies and instead look at a standard deviation change. So what is the impact of a 1 standard deviation change in our x variable? Again, for notational simplicity, we're going to focus on x1, but you could do this with any variable. So what I'm going to define is our z original. So this is going to be beta 1 plus beta 2 x onward and so forth. Now again, these x values, we often look at a representative person, so we often look at the averages, but you could also do this for any individual. You could simply pick their x values. So I'm going to leave this as general as can be. I'm not going to put the hats, but it is going to impact where on this graph you are starting from. But our new z, our z, I'll put standard deviation, we are going to increase, you could also do this as a decrease, increase x by 1 standard deviation. So what I'm going to substitute in for x1 is x1 plus whatever the standard deviation is of x1. We still have the same values for x2 and onward. We can calculate the probabilities for both of these, and we can compare how does the probability look when we've done this increase in our standard deviation for x1 versus where it was originally. So let me demonstrate this graphically. So let's say that this is the starting point that we have picked, this highlighted point. And what we're going to do is we're going to increase x by a standard deviation. If beta is negative, we're moving to the left. We're decreasing the probability. If beta is positive, we're moving to the right. Because our full movement is in z is beta 1 times the standard deviation of x. Beta 1 times the standard deviation of x. That's our movement. So what we have here is our probability with our original values. This is what we're calling L of z0. What we have here is our probability with our standard deviation increased values. And this change in probability, just sort of guesstimating what we have, it looks maybe like it went from 0.2 to 0.4. That change in probability is what we are saying is the impact of a 1 standard deviation change in x. I hope that lecture helped you understand a little bit about marginal effects and how to interpret them. Typically, I would also include the actual interpretation of beta somewhere in these lectures, that it is technically a change in the log odds ratio. That is, I only teach because some people refer to the betas, and I actually want to teach you why that's not a useful or helpful thing. So that may or may not make it into this semester, depending on time constraints. But the important thing to understand here is how to get at an interpretation that is digestible. We want to understand the relationship here between x and y, and in particular, how changing x impacts the predicted probability of y. I hope you're all doing well, and I look forward to interacting with you soon. Take care.